Yeah? What do you think? Can you see?
Should
Okay.
Scoot it back a bit.
Scoot back a bit. It looks like they actually replaced, they got my note. They put it better. This is not the original.
This is. Oh no.
No, neither of these are the garbage originals.
What are you gonna do with that one?
Let's see if I can make a big fucking mess.
Staying
Put that right there. Thank you.
Oh, okay.
Cool. All right.
Just in case we don't watch something.
I got your last assignments here. I got a solution set, but I haven't scanned it and put it up, so I will do that.
Isn't this for the exam?
No, the exam got handed back last
I don't remember.
Oh, yeah, that's due today, isn't it?
I think it's due Friday, but I have
Sure.
it today.
Okay, thank you. Can you give it to me at the end of class?
Sure.
That would be cool. Thank you.
I did it sitting in class some kind of goofy fucking way, so I just haven't done it.
That's cool.
Because I like, yeah, I made an assumption that I don't like, but it made it really easy.
On the recording.
Which looked like not like Facebook. Boo. Boo. Yeah, dude, boo. We're learning new content all the way up until our exam on Friday. And then after.
It's like me with the physics classes. Can't ever stop because we're always behind. Always gotta learn.
Yo, yeah, we're gonna I'm gonna quit. I'm gonna stop talking a little early, and we'll talk about the homework, the current homework.
Could be due today. Just have it done over the weekend.
Is that current homework due on Friday too? Is that what we said?
Yes.
It seems like, yeah, I think it's due Friday, and I think we're gonna keep that too.
One document, guys. Referring to Thomas.
Brendan, I realized I was like looking for yours, and I realized you emailed it to me, so.
I had no
don't have
one.
that
It was just
graded,
like
but I do have.
each page, each document could have separated. It was like one whole page on a document.
That's
So there's like 10 pages of just boom.
Yes!
I tried to do the thing where I like scanned it into like a note
Shit, let's see, this is
and
this.
then like
Yeah, I think-
uploaded that.
I think
and
this
it somehow
packet
like
is yours.
separated
Most
everything.
likely.
I don't know.
That's
And then
freaking epic.
I had like a different
Technology.
screenshot and like a different file for every graph that I had, so it was just like
So,
8
messed up.
different files.
thing you just got back, I have solutions written up, I'll put them up. Just a couple of notes, there was a variety of answers for like the Richardson number 2, because some people were doing some interesting things, which was totally cool. They often didn't work out, but I appreciate going for it. Like understanding that the second derivative is the first derivative formula applied twice. That's, cool. Good shit. Taking the derivative of the derivative. But that often did not work out in a correct answer for algebraic reasons. This was such a stupid fucking set of problems. I hated it. I will never give this problem set again. I hate that it's just like everything's 2 or 5, right? Like even after the Richardson, it's like, oh boy, that was enlightening. So it's a really dumb problem. But thanks for, and even the step size doesn't change.
Doesn't change the
The answer. So really dumb. So thanks for being the last people to ever see that. Number 3, what you were supposed to do there was first derive the general formula for the first derivative using Richardson on F prime formulas with 2 step sizes. In general, 2 step sizes in general, H and 2H. And then work that through and then use that. And then number 4, if I could follow what you did, and the primary place where people lost points here is they didn't stick the 2H or the negative, they didn't put the 2H or negative 2H or whatever into the Taylor formula properly. I think that was the place where people lost. If you have any questions, if you do not believe you should receive the grade you received, let me know. We'll talk about it. Happy to work with you. All right, friends, we have 5 classes left together. Quick note, Wednesday's class, we're not meeting in here. What I think, we could do Zoom, but we could also I could make you a recording and let you watch it asynchronously as you see fit, which I kind of like. And do you like that too?
Yeah.
Yeah, because, yeah, I like it a lot. So I will have that for you by Thursday for sure. And I will have something in it to ensure you've watched it before Monday, or to at least discern if you've watched it before Monday. So you're gonna wanna watch it. Put a little tricky thing in there. I like to put tricky things in occasionally, like every once in a while I'll put extra credit in my homework solutions. There aren't any in this, just saying. But things like that, just to see who's reading them and giving them points for doing so. All right, today I want to talk about the next topic a little bit, differential equations. I want to introduce that to people who have never had differential equations, which would be, please raise your hand if you have not had MT463.
I think it was just me, wasn't it?
Was it just you?
I think so. Yeah.
Okay, well, we're gonna refresh. Nothing better than having a refresher of stuff you know, makes you feel good about yourself, helps the thing solidify, and then it just helps people who have never seen differential equations. But I might actually hook you up with a video or two to watch just to help you get a richer understanding of things.
Be nice for next semester since I'm taking it.
Oh, yeah, yeah, indeed. So we're not going to do anything heavy, but I also kind of think I might give you some insights that you haven't seen. It's always good to see things presented in different ways by different professors, and so maybe we'll get a little insight. Has anybody in here had 463 with me? Yeah, okay, about half the class. Okay, cool. All right. And then I'm going to stop early, and I want to give you time to either finish up the homework, start the homework, ask questions about the homework, whatever. But we're going to stop a little early for that. Does this all sound good? Cool. All right. Very good. So let's start talking about differential equations. Just a bit. Language of science, right? This is the language of science. This is how scientists think in differential equations. The calculus is useful for solving these, but primarily this is going to be the thing we use to describe, let me write this up, used to describe the relationship between the state of a system, and so by state, I mean maybe position, temperature. Those are the only two coming to my brain right now, but those are kind of the main ones. The state of a system in relation to, or the relationship between the state of a system and how it's changing. So I want to start off with a couple examples just to refresh our mind. And I'll tell you this, even if you had DiffyQ, we're going to push your understanding to a different level. We're going to do multi-dimensional differential equations in here. And I know you have not seen that in here. Maybe the 2D ones, you might have done some 2D stuff, but not like 3D, 4D on up. And I'm also going to show you a little trick that will make everything cool. So our focus, and I will define this, our focus will be first order DEs, so differential equations. First order means the highest derivative level is the first derivative. So first deriv derivative is the deepest level of derivative. And when you take diffeq, take MT463, you actually go deeper into this. You go down in second, third derivatives. You solve all sorts of crazy things like that. But one of the neat things I hope you walk away with from this is that even those higher order equations, like a mass spring system, even that can be converted into one of these. The trade-off is I get extra dimensions in my problem as opposed to deeper derivative levels. So if I had a second order derivative in my equation, say a mass spring kind of thing, some oscillatory thing, then, and this is cool, don't worry about it, Daniel, I'll get you there. But if I had a second derivative in there, I could convert that into a first derivative only problem, but I pay an extra dimension. So it's a 2D system in first order derivatives. So our focus will be this with initial values. And the short name for this are IVPs, initial value problems. There are other kinds of problems that are really important. The other kind are boundary problems where you're given some interval you want a solution on, and you know the value at the endpoints, but you know nothing about the middle. Our situation is I'm going to know everything about some initial time. So I'm going to know where I'm at, how fast I'm traveling, maybe how fast I'm accelerating, and so forth, just at a particular instant. And I want to predict where I'll be later based upon that. So let's look at a few examples. Let's start off with a really lovely one, just a very nice one. I also got some code. We'll pop out a little later. Really nice code too. Examples. First one is this equation. I'm going to let T, capital T of little t, equal the temperature of some object. A homogeneous object, like a point object. If it's 100 degrees on the outside, it's 100 degrees instantly all the way through. Temp of an object at time T, and you pick your favorite units. Probably Celsius. Kelvin, we can go Kelvin. That's, yeah, just to let people know where we stand, you know?
We support our scientists.
We support our scientists, exactly. So in some scale. And then T is time. Oh, sorry, this should say little t. Little t and temp capital T of an object at time t. So this right here is what? What is that? Can somebody say that in words? I know you can read it. It's dt dt. Well, yes, ma'am. What is it?
It's the change in temperature over time.
Mm-hmm. Exactly. It's like the velocity of the temperature, right? If yeah. What's that?
Or the acceleration of the temperature.
It's not the acceleration. That would be the second derivative.
Would it?
Yeah. So first derivative is your velocity. Second derivative is generally the acceleration. That's the change in the velocity.
Mm-hmm.
Does that make sense?
Yeah.
Yeah. That's good. I like that. Yeah. That's good. We'll get there. If this thing's positive, what could I say about the object?
It's increasing.
What is increasing?
Its velocity.
The temp.
The temp.
Yeah, the temperature. So it's heating up. If this thing is negative, the temperature's decreasing. That all sound reasonable? And we're just gonna like take this chill and make everybody feel cozy while we either cool or heat the room. So I'm going to put here, there's some constant K. Nope, sorry. I'm going to put a constant T sub 0, and then I'm going to put minus K T. I think that's what I want. Let me just double check my notes. No, sorry, put the K outside. I had it right the first time. I don't have my notes with me. So I guess I'll be honest, I don't have notes. I just thought about this. I'm one of those kind of professors. Lou and I were talking about it. I have a general idea what I want to talk about. I come in, hope to God the passion gets me through, and some experience. So we got this guy right here. Let's say T naught equals the ambient temperature. Just a great word. For lots of reasons. So maybe we have a little picture here. Here's the room. In this room, or this box, or whatever, the temperature in the room is T naught degrees. And then I've got this object here. This is my object. And its temperature is that formula, T of T. Notice here, this is a function. It doesn't look like it because I didn't write of T, but there is a suppressed of T here. So this is literally the temperature at time T. This is the ambient temperature, the surrounding temperature of the object, and this is how fast that temperature is changing. And then we have some initial state. The temperature at some initial time, T naught, is, I don't want to use T naught again, but we'll just put here initial temperature, be a little loose with our notation. Initial temperature at time T naught. And what we hope to do is to be able to create in our minds numerically or in a digital graph something like this. Here's T naught, here's time, and then here's T. And so my initial temperature is right here. And what I want to do is see what happens to that temperature of that object as time moves this way. Does it go up? Does it go down? Does it maybe not even change at all? Does it do something weird? All sorts of options. So we're going to predict the future. Somewhere out there, some cone of knowing. Do y'all know the like cones of light for the possibilities of the future? Have you ever seen this? Yeah, with like quantum theory. I was just thinking about this dog walking the other night. That if we're right here and then the future is this way, you can't travel faster than the speed of light. Like, so theoretically nothing can, so no event can happen faster than the speed of light. So you have this thing called this cone of future possibilities. And those are the only things that can happen that are in here. And then there's this like cool unknown realm back here. And then back here's this cone of past possibilities you could have come from. Check into that sometime, it's pretty neat stuff. But I was thinking, how cool would it be? How do you get out here? I don't know. I think meditation maybe? I don't know.
You have to leave all possibilities. Is it even?
Yeah, that could be too. It's definitely something up here. That's what I'm thinking. All right, so our problem is much more mundane than that. We just want to know the temperature of our potato that we just took out of the oven. So let's look at this formula over here for a minute. I'm going to say that K is also a positive number. So let's assume that K is a positive constant. I think that's right. Yeah, that is right. So, for example, just a few examples about this. If T is less than the ambient temperature of the room, so I've got something that's colder than the room. I just took something out of the fridge and I set it on this table. I would expect the temperature to rise, right? Until it reached equilibrium, which was the room temperature. So, and I see that reflected in this equation. Notice that if T is less than T naught, then T naught minus T is a positive number. And so K, since it's a positive number, then this is also a positive number, and that implies that the temperature of the object will go up. So this means increase T. Just trying to we're just, we're just stepping closely. Let me know, you let me know if anything needs extra explanation. Does that make sense, Daniel?
Yeah, it
Sound
just
good?
looks like physics.
It's just physics. It's just physics. It's not math, it's just physics. Also then, if the temperature T is greater, so I pull my hot potato out of the oven and I set it on that table, then I expect that T minus T naught is now negative. And so that K, T minus T naught, is also negative, but that is the rate of change. So I see that the object is cooling. Its temperature is decreasing. So T is decreasing now. We got our bearings-ish? Nice. Let's make some pictures, because pictures are really going to help with this. Anything we do, we're going to want to see some sort of a graph. So, okay. So I've got a plane here. Woo! Okay. Got a plane here. This is, again, the temperature axis, the time axis. And I want to think about some things here. First off, what is the rate of change of the temperature if at some point I am at the room temperature? So if this is equal to T naught, what is the rate of change? 0, yeah. So if I have something that's already at room temperature, like this table is pretty much at room temperature, feels a little cooler, but for some reason. But if I'm at room temperature, so let's say that's right here, this is again the ambient temperature. If I'm there at some point, T, the rate of change of this solution is 0, and I stay there forever. So notice, let's just make a mark here that if T at T equals T naught, then T of T equals T naught forever. There's no more energy being entering the system or leaving the system. We are at equilibrium. Is achieved. I before E. Okay, there we go. Got it. If I am above the temperature of the room, I expect my solution to go downward. So I would expect a decrease, and I can't go past equilibrium unless there's some sort of extra energy being entering or removed from the system. If I'm below it, I will head toward equilibrium. And I can see all sorts of possible solutions here that would look like this. Corbin.
Is this where, if we're not at equilibrium, can we hit equilibrium still?
Great question. Yeah, great question. So actually, mathematically, no. We can get as close to equilibrium as we want as time goes to infinity, but we can't ever get there. I don't know, how do physicists negotiate that? Because we're going to see the solution cannot ever be T naught if it isn't T naught to begin with. Physics people, how do you reconcile the discrepancy between the mathematical asymptotic behavior of something and then the reality that, of course, that's the same temperature?
If it's close, it is.
It's close, okay. 6 sigmas or something like that.
If it's
Yeah.
Close enough.
if it's close enough, then yeah, it might as well be the temperature.
Okay, cool. So yeah, we can only measure things to a certain precision anyway, right? So nothing is ever exact in this world. Does the Planck constant apply to time and does it apply to temperature, I guess, as well?
Planck's constant is joules over kelvins, I think.
So the Planck constant's like the smallest physical unit. Oh no. What the Planck length? Is that what I'm thinking of? What's the smallest length that can be measured in the universe?
What a funny question.
I knew the answer.
Nobody, we don't have.
Smallest unit?
Yeah, what is
Probably
the
something on
smallest
quantum
unit?
level.
Yeah, definitely quantum, but there's like some sort of minimum resolution to the universe that we're aware of.
The lowest we've done currently, there's a current research problem in CERN that's measuring like the radius of a proton, and that's kind of like, I guess, the smallest thing I can
Sounds
think
pretty
of.
tiny.
Yeah, it's
Yeah.
extremely small.
But then there's quarks in there, right? And they have some kind of.
Yeah, but you can't like physically measure that
Uh.
yet. At least yet. I
Yeah,
don't think anyone's
okay.
tried.
Maybe ever. Huh? Yeah. Okay, so anyway, the temperature will approach equilibrium. Let me show you what a solution to this thing looks like. Does anybody, any physicists or folks from DiffyQ remember whose law of cooling this is?
Newton's law.
Newton's, of course it is, right? This is Newton's law of cooling, in fact. So what Newton observed was the stuff we've just been saying, that if something is hotter than the room it's in, its temperature decreases. And if it's cooler than the room it's in, its temperature will increase. And he literally wrote down a differential equation that made that observation mathematical. That's all it is. Just what we just said is now encoded here in mathematics, in the language of calculus, right here. So that's when I said that this is the language of science. It really is. You observe something, observe its state in relation to its rate of change, create a differential equation relating rate of change to state, and then solve that. So a solution to this, to this star critter here, and let's come up with some kind of letter for that thing. I already used T naught. Should have called it
TI.
Sure, that sounds good. Okay, dig that. Yeah, I like that. A solution to this equation looks like T of T is equal to the ambient temperature, that's going to be there, plus some constant, unknown. This is not, it's related to everything that's going on in that problem, including that constant K. And then I have e to the negative kt. So in some physics classes, probably you take physics with trig, you just get this, right? If you take physics with calculus, you make that, I assume. Yeah, probably. What is the K? Physically, what does the K represent here?
First thing I thought of was the Boltzmann's constant. I don't know if that's true.
Yeah, that's way too fancy for my brain. It might be, I don't know.
I mean, it's a constant, but it's related to the initial conditions.
Yeah.
I don't remember exactly how it's related.
What does it physically represent here? Just looking at this, what is, when K gets bigger here, what happens to this thing as T gets bigger? So for a larger K, so in other words, what is the difference between this and this? Luke?
E to the negative 2t gets smaller faster.
Yeah. So I see this thing here, that lives underneath this one. So this would be e to the negative t, this is e to the negative 2t. So this K kind of represents something about the nature of the object and its ambient environment, like the material it's made out of. Maybe something cools faster. Maybe it's like aluminum versus a hot stone, which would cool more slowly. So the K is kind of wrapped up in the deets of the problem here. But if I were to graph out any of these, they would all look like this. So now this C naught, this C is determined using the initial condition. That word is determined. There's a few letters missing via initial condition. Why is this a solution? Let's just refresh our memory. Why is this a solution? Because if I take the derivative of this formula, plug it into the left side, plug this expression into the right side, they are the same algebraically. So let's just check this is a solution. Today's a very introductory day. I will be ending it a little bit early. So if this is all familiar, enjoy. What a great day. Check this as a solution. So I'm going to compute dt. Hey, could you do that really quick? Calculus savvy? Prerequisite meeting. Friends of mine. I'm not actually looking at anything. I'm just looking at Jesus up here, not here where.
Yeah, we need that right now. Need some Jesus in our life.
Check yourself out here. See if your derivatives are going good. So I'm just going to actually write this in a slightly lovely way. Just commuting the C and the K, pulling the minus out front. Any questions on how I got that? The T naught goes to 0 because it's a constant. The derivative of e to the some function of t is that derivative of that exponent, e to the f of t. Those are the laws I'm using to get that. You will end up doing some calculus for me at some point. The good news is you'll also have all the resources in the world to help you with the calculus, whatever your favorite GPT is, probably. So, now this is the left side. So this is the left-hand side of star. The right-hand side of star, let's figure that out. So it's k times t naught minus my t. So I'm going to plug in that whole solution. And this is a little pedantic, but it's good to just do. And notice here that the t naughts cancel. And I'm left with negative c e to the negative kt. And that is literally, these are the same. And that means I have a solution. I have a formula solution, closed form solution. In other words, in order to compute this derivative, all I have to do is this simple mathematical operation. I've said 3 different ways to think about these differential equations so far. All right. Questions before I erase? Good. Okay, what time is it? Let's see, do I want to say one more thing? Maybe I'll save that for another day. Let's pull up that code real quick. So you'll have to cut and paste it. Again, I'll do the same. It's in a whole new folder called aptly differential equations. Oh, Miss Lavina, where are you? Lavina! Lavina is cringing even in the privacy of her home as she listens to this. All right. Miss you, my friend. I guess I could project this, but we can all just project it on our own. Does everybody have a laptop with them today, or anybody missing one? Okay, cool.
And then which, like, folder, like, assignment is it?
It should be go to content, and then I think on the left side at the bottom you will see a DiffyQ folder. I hope so, Josephine.
Yeah,
Okay.
there's Euler's method and direction field plotter.
Yeah, go to the Euler's method one. That's the code. The other one's an app that we'll take a look at.
Aha.
Aha. Good.
Thank you.
Good. Thank you. Thanks for helping me remember what I did this morning. And I've been avoiding input statements because they just do not play well with the kernel that's used for the web-based version. I'm really stoked. I ordered a new keyboard. It was described as creamy. Yeah, I've never had that. I've never had like a yeah, you know what I'm talking about?
I do know, but I don't have one, but I
Oh.
wish I did.
Yeah, my wife had one, and I was like, "Whoa, what is that sound?" I heard it, and I was, yeah,
So,
yeah. So I've got one coming. Very excited. Maybe I'll bring it in, share the sound, the creamy sound.
Yeah.
It's cool, and it's like a blue gradient, like dark blue at the bottom, fading to lighter blue at the top. Very beautiful. I can keep that clean. I was looking at some pants that were like this light blue, and my wife was like, "You should not own light blue pants." Because I'm always like wiping Cheeto powder on my hand, you know, everything. I just like their napkins as well as essential coverings.
There's some white pants then.
Oh God, no. So I had, when I was a young boy, I had a pair of white shorts. My family used to dress me like a little monkey clown, their little doll. And we were headed to Six Flags. We were going out to Six Flags. And I was like, hold on, before we go, I had to go do something. And we had been playing in the sewer, my friends and I.
Yeah, me too.
Because we would go down there and we would like fish for crawdads. We would like put bacon on a string and then like lure the crawdads and stuff. And then whatever, I'm sure they inevitably died somehow. Poor crawdads. But I had to run down to check a crawdad trap. And so as I wiggled down into the duct on the side of the road, the tar was hot that day, my friends, and the tar was plentiful. So as I slid down, the tar just drug across my shorts in the front, and I returned home completely coated in tar in my beautiful white shorts. So they weren't happy.
It's like clever, isn't it?
What's up?
I think it's from another classroom. It's coming
Oh.
to the
Yeah.
True sound effects. Like,
Oh no,
freaking me out.
it's waking you out.
It's freaking.
It's
Well, the
freaking.
first time I heard it, I was like, am I hearing things right?
I feel like I vaguely heard it the first time.
You
It
guys
sounded-
are
it sounded
huge.
like stomping, and I was like,
I'm reading Cujo too, so who knows what it is. Probably not a rabbit. So many reasons. All right, does this code run?
Yes.
Cool. It's slow though, isn't it?
Not really.
Not really. On your laptops, no. Oh, I'm using a Regis machine, so.
Yeah.
It doesn't even seem to be running here for some reason. Maybe I'll come around and look what you got. So there's let me just point out a few little things you could play with here while I try to figure out why this isn't running. Maybe my kernel needs. No, it's running. I'll just restart the kernel. It's just not doing anything. So there's a Boolean flag, and when I say Boolean, I mean a variable that's true or false that allows you to turn off that arrow field. It's by default on. So if you look in there, see where it says user-defined parameters? It's like bottom third of the code. You see you see your initial time, t naught is 0, your initial position, x naught is 1, and then we're specifying the end of our interval, our solution interval. So this thing here is looking for a function whose name is x of t, the independent variable is t, and we're looking for a solution on the interval 1 to 5 seconds and seeing what happens there. We have our initial condition is at t not equal, it's 0 to 5. It is 0 to 5. So this is our interval that we're looking for. We say that x naught is 1. So this is where we start, right at 1. Try playing with a few different variants of that. And I would also recommend step size, which I'm about to explain in just a second, or I might just do that actually I might just do that on Wednesday for your lecture. But you can turn off that direction field by just setting that to a false with a capital F. It's very precise about capitalization on those things. I think it is. And I don't know why this code is, I'm gonna get no errors. I got no problemo, except Regioso. Oh, it worked when I put it in the second command line. Boy, isn't that pretty code? Let me explain what's going on here, what you're seeing. Because this is our first method called Euler's method, and it's really the most simple way to get a computer to make a picture of a solution for you. We got this, just a little bit, take some deep breaths. We got here, so we got x of t, we got t here. And what you see when you have the Boolean flag set to true, and you see all those arrows on there, what we're seeing are essentially the velocity vectors for any particular state. So let's see, what is my differential equation here? I forgot what it was. It is defined up in the top. So I have that function f of t is -2 times t times x. And then there I've got the example written differential equation, which is dx dt equals -2xt. So that's our differential equation. And what these arrows are, is I'm going to different points in the plane. And I'm setting the coordinates here and computing the velocity at that instant. So for example, let's do dx dt, and let's make a x and a t here. I can go through the plane and I can say, hey, if time is 0 and x is 7, then my slope of my solution at that point, dx dt, is going to be -2 times 7 times 0, and that's just 0. And if you think about it, anytime t is 0, no matter what is here, the slope will be 0. Does that make sense? That no matter what that is. So that's why I see all along this x-axis, horizontal slopes. Slope is 0. Anytime x is 0 and t is anything, I got the same thing. So anytime I'm actually on this axis, the slope of my solution is 0. The tangent slope, my velocity, is 0 all along there. So if I ever actually started here, I would never leave here. Because the way we do these solutions is, we pick our initial condition, say it's like right here. And I look at what the arrow looks like there, and I think they start kind of bending down. Is that right? They're kind of like bend, and the ones down here are bending up. So you see this thing that looks like a current pushing everything toward this horizontal axis. So Euler's method says this: what is your slope using the equation? Set a step size h. Travel that many units to the right, so I'm going to move over h units. I'm going to use just lines, follow that line down to there, using the slope from this point. Now I have a new point in my solution. I look at the slope here, and the slope here maybe looks a little less steep. And so I follow that for h units on the t-axis, and I get my new point. And I just proceed to do this over and over again, stepping by h. And the smaller h is, the more precise my solution will be. Does this sound familiar? Pretty, not too technical, nothing heavy going on. So we've got this solution here on the code, and we see that we do have more interesting behavior than just this, because the slope kind of changes in a really interesting way, so that we see these little bell curvy kind of things coming out of here. Okay, that's it for today. Let's talk about, Christian has a question on the homework. I want to address that. I want to at least have 20-ish minutes for you to get on it, or talk about it, or work on it more. So, let's think about our new ethos. I will not accept anything without a staple in it if it is multiple pages. Everything you give me must have some indication of what you are solving as well. Problem statement, summary of a problem statement, not just instantly like, blah, 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 blah. Bunch of numbers dumped on the page. What the fuck is this? Tell me what this is. All right, that's it. Christian, question, sir.
So for problem 1,
Yes.
because of like the window that we're integrating on,
Yeah.
The first like iteration of the recursive trapezoid rule is like correct out to like 6 or 7 decimals.
It's a pretty flat, yeah.
Yeah.
This is a ridiculously flat, it's almost trapezoidal.
Yeah.
That's okay. We're gonna get it out even further in accuracy. So the fact that you're noticing it's pretty close, great. Carry this out. Because I said 4 decimal
Yeah,
points.
so
Let's,
it's like-
yeah, that was kind of, I was thinking about number 3. Let's up the precision in number 1. How many precision points were you seeing?
Like 6 or 7. It was.
All right, let's do 10. On number 1, go up to 10 points of precision, which we should easily be able to do with a double precision machine. So that should work. Thank you for that. That's a freaking awesome question. That's a man who's done some thinking in compute. So everybody got that 10 decimal places on that one? Thank you. Any other questions so far? Yes, ma'am.
So then for that first question, are we allowed to do the computation on the computer and then just write down what it says? Like for the later ones? Or should it all be?
I would like to see it all written out,
Okay,
if that's okay.
Oh,
Yeah,
sure.
thank you. It's not too bad.
it's fine. I haven't done it yet. So,
You're not gonna tell me.
so I just want to see ahead of time.
Cool. Yeah. So just write it all out, please. Yes, ma'am.
I have a general question.
Uh-huh.
Number 4, do
Yes.
you want us to write out that, or do you want us to use the code?
Oh, I want that all written. That one I definitely want by hand,
Okay,
please.
like both parts, like the 2 and
Oh,
the
yep.
and the 4?
Mm-hmm.
Okay.
Yeah, wait, are you talking about, I'm sorry, did you say number 3 or 4?
I said number 4.
Sorry, I was looking at number 3 when we said that.
Okay,
Yeah, I want that by hand.
okay.
Yeah, and then on C, I definitely want you to go get a precise answer from Wolfram Alpha.
Yeah. I'm-
But these aren't too bad. So just please show me all the steps of it. It shouldn't be too bad. That's a good question. Thank you. Let's do 10 points of precision on that one as well. So 10 points of precision, 10 decimals of precision on 1 and 4 and 2. And then on number 3, all you've got is so everywhere, 10 points of precision everywhere except number 3, where it's impossible to have more than 4. Okay.
Oh, good to know.
Yeah. Thanks. Sorry, I hope you didn't do a lot of work already. And okay, I don't have to worry about that.
No.
Okay, cool.
It's just a good tip to know if I really fuck something up.
Indeed.
If I got more than 4.